In experiment 4, I observed and analyzed the motion of a spring and mass attached to the spring. To predict the spring and mass behavior, I created a model in VPython and compared the model to the actual observations of the spring and mass in the video. From the comparison, I can interpret the changes in energy for the actual data. I found that the model underpredicts the motion of the spring and mass, but this could be due to a lack of inclusion of drag force. Based on Hooke's law, which states the force of a spring is proportional to the distance through which the spring stretches by some constant, which is the spring stiffness, and the energy principle, which states that the change in energy here is equal to the work done on the system, which is also equal to the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared, plus the change in potential energy, which in this specific lab we'll be looking at the potential energy of the spring as well as the potential energy of the gravity from the Earth. Because the system includes the mass plus spring plus Earth, we assume no outside forces are acting on the system, meaning the total work done is equal to 0, and therefore the change in energy is also equal to 0. I entered the given video observation into Tracker with setting the equilibrium length, which is the length at which the spring and mass are at rest, to 0.7 meters for calibration, and setting the origin of the axis to the spring attachment point, which is here, and starting from when the system was released. I plotted the position of the mass on both the x and y axes and saved the position data, which is located here, in a file to display in VPython later on. To model the data, I used a given code outline and edited this outline. I entered in given information about the mass's mass, labeled as ball in this code. The initial conditions were set by looking at the mass's position when first released from rest, here, and using the initial velocity as the 0 vector since the mass was released and the velocity was equal to 0. To find the spring stiffness, which is here, I used the equation for finding the period of oscillation and found the period by finding the average change in time between the full rotation of the oscillating mass and spring and applying this to the equation to discover a spring stiffness of 6.83 newtons per meter. Here we can see that these are the time changes that I used in order to find average period. To find the spring's original length, I used the concept that the force of the spring is equal to the force of gravity, since total work done is equal to 0, and so after canceling the change in position for the work equations, the forces can also be equated, and used the previously found spring stiffness to see a rest length of 0.123 meters. I put this into the code in VPython, and then also I was able to display the changes in energy during the system motion by including the kinetic and potential energies equations, which we saw equaled the total energy, as well as to update the energies total, and also I included the gravity and spring force equations to sum to the total F net and predict the mass and spring position in the model. As you can see, after entering the actual mass and spring position data shown by the red ball, the model, the blue ball, underpredicts the actual observations. This error can be due, like stated at the beginning, to the lack of inclusion of the drag force that truly acted on the system. I can display the changes in energy of the actual system by again editing the code. From the graph, we see that for each period of oscillation, these are each the periods, The kinetic energy and the potential energies of both the spring in green and the potential energy of the gravity in the red line came back to zero. But in between the oscillations, the magnitude of the spring potential energy was at the greatest value for that period, and so was the gravitational potential energy, the magnitude of this value. The kinetic energy, shown by the blue line, at this point went back to zero as the mass changed directions, and at a point where an object changes direction, the velocity is equal to zero. You may ask, is the energy equation satisfied in said situation? As predicted, the energy, which is shown here by the yellow line, is somewhat equal to zero for the entire motion that's displayed, but is not exactly, because again we did not include the drag force which also acted on the ball and spring system. When looking at the way we determine the period in the code, we use the y position graph, but the period of oscillation for the x position graph is different. This is because the mass oscillates in a horizontal elliptical pattern, which means the change in x position of the mass will be smaller than the change in y position, and therefore it would take a smaller amount of time for the mass to reach its initial x position in a rotation.